So welcome everybody again. It's my pleasure to introduce Catharina's talk for today. The first one I can say has just a reminder about the tutorial sessions for today. So go ahead.
Okay, thanks very much. So today I want to talk about backgrounds or a little bit motivation for categorification. So what I want to talk about is starting from classification problems, classical classification problems, to more abstract structure, and somehow sell this as a basic categorification example. So that's the plan. So let me start with classical problems. And some of them are extremely easy, but extremely useful. And some are not so easy, but also useful. Okay, so let's try to classify finite sets up to isomorphism. So I take finite sets and ask how many finite sets are there up to isomorphism. So when I have X, a finite set, then of course it's isomorphic to another finite set if and only if they are in bijection to each other. So there's a bijection from one to the other, which means they are isomorphic if and only if they have the same cardinality. So I can take the cardinality of the set. And so my classification problem is solved by saying it's classified by the natural numbers, including 0. Okay, now let's do another example. I can take K any field and ask the question, what are finite dimensional K vector spaces up to isomorphism? And so the answer is, of course, very similar. Two finite dimensional K vector spaces are isomorphic if and only if they have the same dimension. So I can just take the dimension. Again, I get a natural number or 0, and this gives my classification problem. Now let's do a bit more complicated example. So let's look at compact closed one manifolds. So we want to classify them up to isomorphism. And this sounds much harder, but actually I claim it's the same classification answer. So it's again classified by N0. And if you don't know what compact closed one manifolds are, I just tell you the classification is so that if I take a natural number, then I give you a one manifold, which hopefully everybody knows, namely a circle, as one, and I just take n copies of them. And then the little theorem says that this is all what I get if I look at compact closed manifolds, one manifolds up to isomorphism. So let's do another example. I want to look at finite dimensional representations of, say, the Lie algebra SL2C. And I do this over complex numbers. And again, everything up to isomorphism. So what is SL2C? SL2C, so this is just matrices, 2 times 2 matrices with complex entries, which have the property that the trace of A is 0. So a representation is just a vector space. A finite dimensional representation is just a finite dimensional vector space with an action of SL2. So every matrix acts by a linear endomorphism. And I want to have some compatibility with the structure. So what I want to have is that the commutator of such matrices in SL2 should be mapped to the commutator of the corresponding endomorphisms. And then one can classify these finite dimensional representations again by taking a representation V together with the action of SL2, denoted like this, and I send it to the dimension. And the statement is for every dimension, there is exactly a unique finite dimensional irreducible representation of this dimension. Okay. And one can write them explicitly down. If you don't know this, we can do this in the exercise. So let's do another example. I want to fix a prime number P. And I want to look at finite abelian P groups. So groups which have order P to the something. And I want to take them indecomposable. So then you look at the classification of finite abelian groups, and it turns out that indecomposable finite abelian groups are just of the form Z modulo P to the nz, if they are P groups, up to isomorphism. And so what I can do, I can just take the exponent n, and what I get is again that the classification of these P groups up to isomorphism is again given by the natural numbers, including 0. Okay. So let's do one more example from topology side. So let me take compact closed orientable two-dimensional manifolds. So that means these are surfaces without boundary. So we would like to understand what they are they up to isomorphism. And isomorphism here really means homeomorphism, which I don't want to explain, but that's the correct isomorphism notion here. And so here I give you an example. The sphere is such a thing. So it has no boundary and it's two-dimensional, it's a surface. But other examples look like a torus, or more generally something like this with a few holes. So on the classification is just, I just count the holes. So in this case, I would send it to 4. In this case, I have no hole, I send it to 0. And in general, I take such a surface and I send it to its genus. And what I get is a natural number, or 0. And I get again the classification given by the natural numbers, or 0. Okay. So now let me finish this examples list with an algebraic example. I want to classify modules over a polynomial ring in one variable. And where x, this variable x nilpotently. So x to some power, it could be really big, but it has to, when I take a big enough power, it has to act by 0. Yeah. Do you have a question? So then I can take finite dimensional, indecomposable, nilpotent modules. And again, I want to take them up to isomorphism. So the claim is, this is more or less the Jordan normal form over the complex numbers. So I have X a nilpotent endomorphism, and then these nilpotent finite dimensional nilpotent representations means just I say how big a Jordan block can be. And this gives me a number, a natural number. And the claim is when I take M, a representation, or such a nilpotent representation, I take the dimension of M. Or if you rather want to think in terms of module theory, you would take the length of M. This gives you a classification. Okay, so I hope you understand some of them, and the ones which you don't understand, we can discuss. But let's just accept for the moment that we have all these classification theorems. Right, so now I see that what I classify is, or what I get as an output out of the classification is always the same thing, namely natural numbers, including 0. And then I can ask the question, can we see more structure of natural numbers on this side? So for instance, so we realized N0 as somehow isomorphism classes of something. So can we see, whatever C means, the addition of N on this other side? And this other side in all these 7 examples is pretty different. But the question is, can we see the addition which is on N0? Can we see it on the other side? So on some of them, so you saw already in Monica's lecture. So here is again my list so that you can see the list. So let's look back at number 1. Number 1 was finite sets. And I claim yes. And this is the example you saw in Monica's lecture. Here we can see the addition, because we took the cardinality of a finite set. If I have two finite sets, X and Y, I can take the disjoint union, and the cardinality of that is the sum of the cardinalities. Okay, so this is addition. Maybe I'll make it a bit smaller. Yeah. So finite dimensional vector spaces, I claim yes, we can see addition. Namely, I take the dimension of the direct sum of two vector spaces, say V and W. And so this is the dimension of V plus the dimension of W. Perfect. Compact closed manifolds, these are just circles. So if I take the disjoint union, of course, I add the number of circles. Now, finite irreducible SL2 representations, this is the same thing as with vector spaces. I can say yes. I just take the sum and I get the dimension of V plus the dimension of W. But wait, I was not careful enough because I assumed irreducible SL2 representations. If I sum two irreducible ones, if not one of them is zero, this thing is definitely not irreducible. So I cannot really do this. So this is a good candidate to take. But I get outside my set. So it doesn't really work, but maybe one has to adjust it and then it might work. Okay, let's go to the indecomposable finite abelian groups. Okay, I can take the product of cyclic groups. But again, this is in general not indecomposable. So again, I have this yes, which doesn't really work. I have a candidate, but it doesn't give the precise answer. Then I had these compact connected oriented surfaces without boundary. Here I can take the disjoint, the connected sum. So yes, in this case, I can take the connected sum. So what does connected sum mean? I just cut off the top piece, the head somehow, of one of these manifolds, and I cut off the other one from the other one, and then I just glue them together around a circle. And what I built for you then is something which has the number of holes equal to the number of holes from the first surface plus the number of holes of the second surface. So this is fine. So this works. And now the last example, for finite dimensional indecomposable CX modules, I have again the problem. It looks like it would work, the direct sum. But again, in general, not indecomposable. General, not indecomposable. So I'm again outside my set, so this doesn't really work. Okay. So then, of course, the natural numbers also have the multiplication, but let's look at this a little bit later. Let's first continue with addition. So what I want to do now is form addition, or formulate, maybe I should say formulate addition in general categories. So whatever addition means. Okay. So and as a warm-up, or the example which we really all should know, is the vector space example. So we saw when I take two vector spaces, I take the direct sum of vector spaces, then the dimensions add up. So what does it mean to take the direct sum of vector spaces? So say x1 plus x2 of vector spaces over fixed field K. Okay, so this means I claim the following. This means another vector space, let's say set, together with the following thing. So I don't tell you the elements in this vector space. I tell you maps between this vector space. So I tell you that this vector space, which I would like to think of as x1 plus x2, has the property that x1 embeds into this vector space. So if you think you have x1 plus x2, then of course x1 embeds. Also x2 embeds. So I have linear maps like this. And then of course I can project onto the first vector and I can project onto the second vector. And I have relations. So I have the relation if I embed one of the vectors via ij, j could be 1 or 2, and then I project via the corresponding same j, then I get just the identity on this vector space xj for j 1 or 2. And the other thing is when I project first to the first vector, and then I include back again, plus I subject to the second vector and I include back again, what you just get is the identity on the big space. So these are the two things you can check hold, and let me call them by a plus. So these are linear maps which hold for the direct sum of vector spaces. So and we can deduce from this things which you might want to write down when you define a direct sum of vector spaces. So you can, for instance, deduce from these properties that ij is injective and pj is surjective. So the inclusion is injective and the surjection is surjective because this property says, this composition says that we get the identity. So better the first map should be injective and the second map should be surjective. Okay. And another thing which you can, for instance, check is when you take the first inclusion and you take the second projection, then I get 0. Why do I see this? So let's play a little bit around with this. So I1 followed by P2 is the same thing as I sneak in the identity. So, but I sneak in the identity written in this very complicated way here. Okay, so I sneak it in and I pull it out immediately via this sum. So I get pi2 I1 composed with P1 composed with I1 plus P2 composed with I2 composed with pi2 composed with I1. So this is just the identity sneaked in. And so what I get is, because this guy is the identity and this guy is the identity, what I get all together is 2 times P2 after I2. And so I wrote my map is equal to twice my map. And then of course, it follows that my map is better 0. And of course, you can swap the indices and look at P1 composed with I after I2, and you get the same, by the same arguments also 0. So you can just deduce from these small properties, I guess all the properties you would expect from the direct sum and maps between them. So now let's formalize this. So an abstract notion of formalizing this is the notion of an additive category. So an additive category is by the definition a category C, satisfying the following thing. So property 1 is additive 1 for all objects, x1 and x2 objects. So if you are not happy with categories, just think of vector spaces. For any 2 vector spaces, the maps, so HOMs between these 2, has to be an abelian group. So like maps between vector spaces form an abelian group. And the second property is I want to have an object, which I call 0, such that when I take HOMs from this 0 object to anywhere, I get just the trivial group E. So the group is one element for any object X. So if you want to have an example, if I have the zero vector space, I have a unique map from the zero vector space to any other vector space. Okay, and now the third condition is we want to formalize addition. So this is the important thing. So for all objects x1 and x2, I want to have a direct sum analog. And I just say there exists an object Z with morphisms exactly as we had above. With morphisms I1, I2, P1, P2, satisfying this condition which we had above. So I look back, I have a map I1 like this, a map P1 like this, I2, P2, and they should satisfy these conditions which we had before. But now they could be in a very abstract category. Okay. Yeah.
Just as a note, in the computation that you did above at the end of the previous page is 2 times P2 composed with
I1. I did a typo. Is this the problem?
No, it wasn't a problem, but just like since you're gonna share your notes, so it's clear.
Yes.
For
perfect.
Thank you.
Thanks. Good. So now the remark is, if we have a x1 and x2, then this set, which I could also call set x1, x2, set x1, x2. So this is unique up to actually a unique isomorphism. And we called it just a direct sum. Although it might look very different from a direct sum of vector spaces. And you can write down this map explicitly by thinking of I can go from a set to the other set by going first to x1 and x2, and then afterwards with the other inclusions to a set primed, or vice versa from Z primed via the first projection for Z primed and second projection to Z primed to here, and then compose with the corresponding inclusion, and they give you isomorphisms from Z to Z primed or vice versa. So this gives uniqueness, so we can talk about the sum, and we call this the direct sum. Okay, and another remark I want to take, if we don't assume that these direct sums exist, so if we only have the category C with only this first condition, so that home spaces form an abelian group, we can formally add the zero object. So we just throw it in and direct sums. And turn this C into an additive category. So this is the smallest additive category which contains C. So the smallest additive category containing C. So when you look back at these examples which we had before, sometimes we didn't have a direct sum, but we had an idea what the direct sum should be. And it turns out when we just show it in formally, then one can show that as a result of this throwing in, we get a category. So for instance, let's say in this example of irreducible SL2 web stations, if we do this formal construction, we would construct a category where we formally throw in something, but it's equivalent to the category where we just remove irreducible and look at all SL2 finite dimensional web stations. And then we can we are fine with forming direct sums, and we can categorify the addition in natural numbers. Okay? So this is totally abstract nonsense, but in all the examples, so for instance, the additive closure in example 4 is equivalent to all finite dimensional SL2 representations. And in 7, for instance, this was this nilpotent representations. This is what we get, finite dimensional nilpotent CX modules. So before we had only indecomposable ones, and then when we take the direct sum, we cannot get anything indecomposable. But if we pass to all of them, the direct sum made sense. And this is exactly a category which is equivalent to this additive closure. So intuitively, it does what you think one should do. Okay, now, as Monica already said, often we would like to linearize. So we are not so happy with abstract categories. So I want to linearize. So let K be a field. For me, often the complex numbers, but you can define it in general. So a category C is called K-linear if for any objects x1 and x2. When I look at the Hom space from x1 to x2, that this is not only a set, but it's equipped with a K vector space structure. And the composition should be K bilinear. And at least for me, in real life, most categories are K-linear for some K. So for instance, K vector spaces and linear maps. Or finite dimensional K vector spaces and linear maps are such an example. Then you can also take modules over a finite dimensional algebra, A mod. So this is finite dimensional A modules for a finite dimensional algebra. If you like this, so for instance, a group algebra of a finite group, then modules over this group algebra form a K-linear category. Yeah, I can also state this explicitly, representations of a finite group. You can also remove finite and look at algebraic groups or Lie groups, whatever you want. You can take representations of a Lie algebra. You can take representations of a Hopf algebra, whatever you like. And I bet most representations you ever looked at are from a linear category. Okay, and a nice thing is, whenever you give me a category, so given a category, which is reasonably nice, and by reasonably nice, I mean satisfying this condition, which I called additive 1 before. So recall additive 1 was a category where the Hom spaces are not only sets, but form an abelian group. Then we can always linearize it by taking the original Homs as a basis of the Hom space and turn it in this way into a vector space. So this is maybe an abstract remark at the moment, but we will use this very explicitly a little bit later to create many K-linear nice categories out of easy categories. So and we should extend the composition in a bilinear way. So the upshot is whenever you have some reasonable category, then you can also always turn it into k-linear category. So here I want to give you one example so that you can see one explicit thing here. So I want just to look at the category C with one object and two written in words morphisms. So here's my object. And I have one morphism, which is just the identity, which I should always have. And then there's another one, which I just call S. And I want to have the composition. Of course, everything composed with the identity to whatever it was. I only have to tell you what is S composed with S. And S composed with S, I want to say it's the identity. Okay. So this is something like the morphisms form the symmetric group S2. And now let's linearize it. So linearize means I have, again, a category with one object. Oops. One object here. But now the endomorphisms of this object in this new category, they form a vector space. And it's just a linearized version of what I had before. So I have a vector space, which has a basis given by identity and S. And then I multiply in the way how I multiplied before. So I get nothing else than the group algebra of the symmetric group S2, which we saw in the previous talk. So that's a baby example how we linearize this category, which just had two morphisms. Yeah, I want to give you another example. So the other example is the category, which I want to call TL. This stands for Temperley-Lieb. I want to put a bar above it because I want to change it slightly a little bit later. And it depends on a number, which in this case is 1. So what is this category? This category has objects, just natural numbers. And I think of natural numbers here. So let's say A being the natural number as putting A points next to each other. So this is supposed to be A points. Not A point, but A points. So the number of dots is A. And then I have to say what are morphisms between them. So now, I want to define HOMs from A to B in a diagrammatical way. So for instance, let's say A is equal to 2 and B is equal to 4. So I want to tell you when I have 2, which I think of as being 2 points, and 4, which I think of being 4 points, I have to give you morphisms going from 2 to 4. So this, I should give you a set of morphisms. And this set, I want to say, are crossing-less matchings of A with B points. So what does crossing-less matching mean? So this means I take my points and I connect any point with one other point, exactly one other point, in a way so that these strands don't intersect. And these strands all happen in a little rectangle, like this. So here's an example. So every point is connected to one other point, exactly one other point, in a way so that I don't intersect. So let me draw you a few more of such morphisms. So here would be another example of such a guy. I connect without crossing. This is another one. Here's another one, which doesn't have any strands going from the bottom to the top. And here, I want to show you one guy, which is not allowed. So this is not allowed because the strands cross. So this is not allowed. So, and I claim these are all the examples you can do of morphisms, crossing-less matchings, from 2 points to 4 points. So check it as an exercise that these are all. And so this I want to take as a set of homomorphisms from 2 to 4.
Catharina,
And yep.
Could you have the one that is nesting on the top row?
Did I forget one? Yes, I forgot one.
Okay.
It should be fine. You're right. It should be 5. You're right.
Okay.
So, because, why should it be 5? So behind all this, there's nice combinatorics, really beautiful combinatorics. And the number of crossingless matchings is a really famous number. And it's given by a so-called Catalan number. And indeed, the Catalan number is 5 and not 4. Okay. So I just refer you to lots of exercises, combinatorial exercises, which show you really the beautifulness of this category. It's very simple in somehow in defining it, not abstract, but beautiful. So, and what is the composition? So I have morphisms now, but I have to compose them. So the composition is very easy. It's concatenation of diagrams. So let me do an example. Here's an example of what I mean by concatenation. So I think when you work with diagram stuff, it's always much better to give an example instead of writing down a very formal definition. So if I have this diagram and the other one, so first of all, I can only compose like morphisms so this would be a map from 1 to 3. And then the next map, which I want to compose afterwards, has to start with 3 and can go somewhere. So 3 here and 3 here, they have to match. But in this case, they match. And so what I do, I just concatenate them in the sense I put them on top of each other and put them together. And because the first one ends at 3 and the second one starts at 3, I can put them together. And then I just make them straight because I only care about the connections. So I get, for instance, this composition. And so this is a beautiful snake. I maybe didn't draw it beautiful, but this is a very beautiful snake. And you should remember this one. And here's one more example. I can take this one, compose it with that one. Again, I check, I end at 4 points with the first map, and I start in 4 points with the second map. What I do, I concatenate them. But now, however, I somehow move it around or something, this will never be a crossingless matching in my definition because I have this stupid little circle here, which somehow is really bad. So what I want to do, I concatenate diagrams and ignore internal circles. So I just say this is equal to that guy. So I ignore this internal circle. And what I get is a crossingless matching. And so the claim is that this defines a well-defined associative multiplication on my composition of maps. And you can linearize now. Can linearize to get what I want to call TL1 without a bar on top. So by definition of linearization, it has the same objects, namely natural numbers and 0. And homomorphisms in this linearized category from A to B is given by the K vector space with basis crossingless matchings from A to B. And then the multiplication is just the multiplication from before on basis vectors, extended K-linearly, or K-bilinearly, I should say. Okay. So what we defined now is an abstract notion of what does it mean to have direct sums, which is supposed to be the analog of multiplication in the natural numbers from our examples before. And we had this abstract nonsense of turning a category into an additive category, and abstract nonsense to make it into a K-linear category. So, but let's go back to the beginning. can we see multiplication? And see again in quotation marks. So I want to go back to this examples. And the question is, can we see multiplication? So maybe I take green. So in finite sets, indeed, we can take multiplication as being the product, because when I have the product of x two sets, x and y, the cardinality of that is, of course, the cardinality of x times the cardinality of y. Perfect, we have our product, as in Monica's lecture. Then finite dimensional representations, we already learned the multiplication is tensor product. So V tensor W, the dimension of this is the dimension of V times the dimension of W. So this is for the second example. For the third example, I have to admit, I don't know. So if you know a good interpretation of multiplication, let me know. I only found very stupid ways to do it, which are very artificial. So I gave up. So I think there's none, which is nice. Irreducible SL2 representations, like for groups, you can tensor representations of a linear algebra. Again, it's a tensor product. So V tensor W, the dimension of this, is the dimension of V times the dimension of W, and SL2C acts on V tensor W if it acts on V and on W. Okay. Number 5, I have no idea. Again, I don't know. Number 6, you can build some sort of funny multiplication by just stacking some sort of surfaces on top of each other, but I don't know anything really nice. But let's look at the last example. We want to take the tensor product, the multiplication in this category of, say, indecomposable CX modules, or at least inside CX modules, which are nilpotent. And so what I can do is I can do the following. I can take M and N nilpotent CX modules. What I can do is I can tensor them together over the complex numbers. And then, of course, the dimension of M tensor N over the complex numbers, just as a vector space, is again the dimension of M times the dimension of N. But wait, why is the tensor product of two CX modules again a CX module? In general, if I take the tensor product of an A module with an A module, it's not an A module. But here, in fact, it is. So it is a CX module because of something very important, because CX is, for instance, a Hopf algebra. And if I have a Hopf algebra, CX is Hopf algebra. So Hopf algebra means, in particular, there exists an algebra map, which is called delta, going from CX to CX tensor CX. And as we had before in the for finite groups, this CX tensor CX acts very nicely on here. So I can just act with CX by first taking an element here, map it over there, and then act. And so that means this tensor product becomes a CX module. And then I leave it as an exercise. I think that's a very nice exercise to check that it's indeed nilpotent.
Catharina, in the chat, Maya asked a very good question in the SL2 case.
Yep.
That whether when you tensor together irreducibles, will the answer be irreducible?
Okay, that's a perfect question, and I should have said this. So we have the same problem as when we add two things together. So indeed, this is in general. I should warn you. This in general not irreducible. Very rarely it's irreducible. And it's very, very difficult problem usually to decompose this into irreducible or indecomposables. And we again are in this situation where I should say yes, but not really, because we have a candidate for multiplication, but we have the problem it gets outside of our category. Yeah, thanks for this question. It's a very good question. Okay, in this example, the Hopf algebra structure, for instance, comes from seeing Cx as a universal enveloping algebra of a abelian Lie algebra, and then this gives an example of a Hopf algebra. But you might find other explanations for this. Okay. Any other questions?
There has been a question that I think is a good moment now to ask, now that you stop. And it was related to the DIT exam. And someone is Lydia asking this question. If you want to unmute yourself and ask it directly.
Yeah, so I was wondering, in the definition you provided of additive category, if the direct sum you defined is equivalent to existence, or like if it's equivalent to existence of finite products and coproducts.
Yes, yes, it is.
And is that like some kind of clear equivalence, or is there a lot of work to do between them?
In between. So it's a pretty standard, it's clear if you are not a total newcomer to these sort of things. Yeah, it's not difficult. It's standard arguments.
Okay, thanks.
But I didn't want to say too much about products and co-products in general.
That makes sense.
So, and what I also wanted to emphasize, which is very important when you do categorification, you give up talking about objects and rather say what are morphisms between them. So if you observed, I carefully avoided to say what is x plus y, really, in an abstract category. I only told you this is some object which we don't even know how it looks like, but it has the following four maps, and these following four maps have the following relations. And this is some way of thinking which is very useful for categorification. So you characterize things not by their elements or something, but by their morphisms, or morphisms going to other stuff. Okay, so we saw now that sometimes we can have a multiplication, sometimes not, and sometimes we have a multiplication if we allow to change the category slightly or do some trick which we don't understand yet. But let me first formalize what it means to multiply two things in a category, or to have an analog of tensor products in general. And this is the notion of a monoidal category. So a monoidal category is somehow, for me, the general nonsense notion for having a category with tensor product. So a monoidal category is a quintuple consisting out of C, X, A, 1, and I. So maybe I should warn people who saw a monoidal category somewhere that I might give a different definition when you look at it, but it's equivalent to what you find wherever you found the other one, I would guess. So if you are not happy with categories yet, then I give you here, parallel to the definition, an example. So if you don't know categories very well, you should think about sets, or you think about k-vector spaces. And for each step, I will tell you what the abstract nonsense mean in this example. Okay, so where C is a category. Well, this I should maybe write. Yeah, C is a category. So for instance, sets or vector spaces, something like this. And then this tensor is supposed to be a functor from C times C to C. So it sends a pair of objects to something, to an object, which I denote by x tensor y. So in my example, for sets, I take a pair of sets, x and y, and I just take direct product. And if you do vector spaces, then I take x and y, or maybe v and w, maybe better for vector spaces, v and w, and I send it to really the vector space tensor product of v is w. And then I have maps, f and g, and I just send them to something which I denote by f tensor g. How does it look like in the example? Here I take two maps between sets. I just take the product. So f acts on x and g acts on y. And in vector spaces, I take f and g and I really send it to the tensor product. Okay. So, and then what I want to have for all objects, x, y, and z, I want to have a map, which I call the associator, AXZ, which is a natural isomorphism. Which goes from x tensor y, although I don't really know what tensor is, but this abstract functor x applied, this tensor functor applied to x and y. So I do this first here, and then afterward with z, or I can do it in the other order. I first do y together with z, and afterwards the x in front of it. So, and the claim is there should be a map, which is a natural isomorphism from the first to the second. So let's do this in the example. In the example, I have 3 sets, x, y, and z, and I can take the product of x and y, and take the result, take the product with z, or I can take the product of y with z, and take this thing with the product of this thing with x at the front. And of course, in this case, they would be just the same thing, so I have the identity map between them. In the category of vector spaces, you can take the tensor product of v and w, and afterwards tensor product with z, or you can take first w with z, and then tensor in the front with x. And of course, there's an isomorphism going between them, but you have to write it down what it does on basis. And so the best thing is if you write it down in basis, but you might choose a basis, and so it might depend on something. But there is such an isomorphism, and it's of course natural in V, W, and Z. Okay, so I call this the associativity isomorphism. And then I also want to have an object 1. So an object 1 which somehow behaves like a 1 for multiplication, but now multiplication replaced by this funny tensor. So what is the object 1 for sets? So when I ever take the Cartesian product with the empty set, nothing changes. And if I take the tensor product with the field, nothing changes. So I want to define 1 to be the empty set here, and 1 to be the field here. And then I want to have an isomorphism. Say I going from 1, tensored 1 to 1, which in the category of sets, of course, is when I take empty, tensor empty. So and tensor in this case is the product. This is of course the empty set. So there's nothing happening. And if I take K tensored over K with K, I get something which is isomorphic to K. Okay? So this is now the abstract nonsense of defining a monoidal category. And the idea is that this funny tensor product, which might look very different depending on which world you are, is supposed to be a categorified version of this multiplication in, for instance, natural numbers or N0.
There is a question, Catharina. Dusa is asking if you have the empty set times A, if that is equal to the empty set.
So you have this. This is something which you have to deduce from these axioms. And I need some properties, which I haven't written there. But at the end, you can show that empty set times something is something. But I don't put it in the defining axioms. It will be a consequence for me.
Okay.
This is one of the things where I think my definition might differ from a definition you find in the internet. So I'm following this book of Ettinghoff, Gelacki, Nikšić, and Ostrich. they have this definition, and I think it's a much better definition than the one you might find on Wikipedia, for instance. But we will have in the exercise problems many things of the form deduce from these axioms some of the axioms you find in the normal literature or in standard literature.
Thank you.
So, but what I didn't write down is now axioms which they should satisfy. They should satisfy two axioms. The first one is the so-called Pentagon axiom. And so this is something very important for categorification. So we have as an input datum, we have a few things. We have some objects, and we have in particular these maps depending on X, Y, and Z. And now this Pentagon axiom goes one level higher somehow and says we want to have some coherence conditions between these maps as well. And so what does it mean? So this is the following. So we take some of all possible bracketings of 4 elements. So here is one of them. Here's another one. That's another one. So then I have W tensor X tensor Y tensor Z. And then I have W tensor X tensor Y tensor Z. And then here we have W tensor X tensor Y tensor Z. So this is different ways how I can tensor these 4 elements together in different order. And for each of them, I have the corresponding A. So, and I leave it to you to put the indices. It's already a nice exercise to put the indices, which I have to put there for my A. And here's A. Again, some indices. So, and the Pentagon axiom says that this diagram commutes. So in other words, it doesn't matter whether I start from here, take this A, and this A, or whether I start from here and take that A and that A, I get the same map. Okay. And then the second thing is the unit axiom. And the unit axiom says, if I look at this functor, which takes an object X, so this is slightly related to Dusa's question, and send it to 1 tensor X, respectively, I take X sending to X tensor 1. So this is somehow left multiplication, and this is right multiplication with 1. They define equivalences of categories. So this is the analog of multiplication with 1 is doing nothing, is a much more complicated statement in terms of categories. So and I think I have maybe 2 minutes. So let me just finish with mentioning some examples of such monoidal categories. So, and I'm cheating. So I said a monoidal category is a quintuple, and I only have 5 minutes. So I don't write too many quintuples. I only write for you the category, and I leave it to you to find out what the other 4 things are in the quintuple. So I write only C and find the other 4 guys somehow. Okay, first example I want to give you is Web G. This is finite dimensional representations of, say, a finite group. Some people here definitely like algebraic groups. So algebraic group or Lie group. And you can work over an arbitrary field. These are from a monoidal category if you put the correct other 4 things. So, but with the normal tensor product of representations, which we saw today already, representations of a Lie algebra. With the example which I gave upstairs as a special case for Kx as a Hopf algebra. So the universal enveloping algebra is a Hopf algebra. So we can take tensor products of representations. And then I will mention some things which will come in the next lecture, namely this Temperley-Lieb example. So this TL1 is monoidal. And this will be a very nice monoidal category given by diagrams. And then there are things like the category of tangles, which comes up in knot theory or topology, etc. But I should warn you, and this is why I say I'm really cheating, the associativity morphism is not unique. It's not unique. And it might be, and sometimes, not the obvious one. So in the examples I gave you, it's always a question what obvious one means. In the examples I gave you, I think most of them are the obvious ones. But we will see in the exercises that there are, for instance, on the category of representations of a group, there are associativity maps, these associators, which I defined upstairs as an input of monoidal category, is not the obvious one which you think. And you can construct quite different monoidal structures on the same underlying category. So I'm really cheating when I leave these 4 guys out because they're absolutely not unique. And I should really specify them. And let me finish with the upshot. So the upshot I want to finish with is an additive monoidal category is a maybe categorification. So I put it in quotation mark because the whole point is really to make this word a bit more precise, but intuitively think of it as a categorification of a monoid. So for instance, in our case, this monoid N0, which I gave at the beginning. So this is the upshot, how you might want to think about monoidal categories. And now I stop here. Sorry for overrunning 2 minutes.
No worries. Thanks, Catharina, again.